Okay, so thank you all. I know some people are still getting coffee, but you know, if I talk loud and they leave the door open, they'll hear this as well. So this is work with Yuna Lee. She's not here today. This was funded by the NSF SciSip program, so a shout out to NSF. This paper was recently published in Research Policy, so if you want the full version that doesn't squeeze within the 15 minutes, you know, you can read that. So the question that we're interested in here is sort of more understanding of the innovation process. We begin with the economics of innovation, but the point here is that while this is the sort of canonical view in a lot of the models of innovation, what we're trying to do is sort of broaden this by incorporating the sociology of work and organizational learning, and talk about how innovation is generated throughout the firm, not simply in the R&D labs. You know, I didn't put up here, but the vast majority of firms in the US do know R&D, but there's a lot of innovation that comes out of those, and more interesting, or in addition, a lot of firms that do R&D, and we'll show this, generate innovations from other parts of the firm besides the R&D lab. And so what's the specific model part of this is, besides the descriptions, is how do the characteristics of the knowledge environment in which the work is embedded affect the relative rates of R&D and non-R&D innovation. And the idea here is to ground our models. This has sort of been a theme in the day, to ground the models, in this case of innovation, in the practices in the firm, and incorporating both the R&D and non-R&D innovation. I'm not quite sure how it is. So we want to, one, understand the fundamental drivers of innovation, more broadly conceived, and in particular, how does the organization of work and choices of technology affect organizational learning and innovation? And you know, from a managerial point of view, how you could build a learning organization to promote an innovation economy. Just two quick examples. One example, because what do you mean by non-R&D innovation? So here was an example. We interviewed a salesman, worked for an industrial supply company. There was this need for a cleaning system related to fiber optic connectors. He had some ideas that we need something on this, and I might know how to do it. And the R&D lab basically said, this isn't your job. We do the innovating, you do the sales. But he wanted to pursue this. He ended up making basically one-man skunk works. He came up with a good solution to the problem. The firm ends up patenting it, global, US, Japan, Europe. This becomes a major line of business for the firm. Another example, this was the technical service rep for a specialty chemical company. There's a problem with ship coating. It was sort of standard coating, but it turns out it's toxic. And so using his background in chemical engineering, he comes up with a better coating. This also triadically patented, also becomes an important strategic business for the firm. So these are the kinds of things that we're talking about. And in particular, what we're interested in is how the nature of knowledge affects the relative rates of learning across different parts of the organization. The two sort of dimensions we look at are the generality of the knowledge and the visibility of the knowledge. So in terms of generality, you can think of the periodic table as a sort of canonical example of a generalized version of knowledge that's applicable in all places and all times. And then if you actually looked at a chemical factory or a paper plant, this is an example of very sticky, embedded application of knowledge. So the argument here is that to the extent the knowledge base of an industry is more general, more mobile, more abstracted, that the relative rates of innovation between the R&D parts of the organization and non-R&D parts of the organization will favor the R&D. In contrast, we think of the visibility of knowledge. So, example from woodworking or from mechanical industries, and are relatively high visible knowledge. And then it turns out chemical plants or for example, semiconductors, the visibility of the knowledge is lower. And what we mean by visibility here is, first, can you actually see the thing, as like in the case of woodworking or in the case of mechanical, but also the extent to which there's tight links between your actions and the outcome, where in some cases there's a sort of black box and you're not always sure what happens. This turns out to be true in a lot of education technology, for example. And so if it's a tighter link, you learn more rapidly. And the argument here is, although both R&D and non-R&D benefit from visibility, that the ratio will favor non-R&D. So if it's visible, non-R&D should be relatively higher. If it's general, R&D should be relatively higher. The data we use, ideally what we'd want is to be able to observe a bunch of people, like the first thing where we wire everyone up and follow them around for months or years at a time. And then what we want is, when did they spark an innovative idea? Unfortunately, that for now is unobservable. So instead, what we do is we start with a large sample of inventions across a lot of different knowledge environments, using project level, not firm level data, and then back into that to figure out how these are sensitive to the knowledge environment. So we have a survey of inventors in the US on patents that were triadic patents in the US, Japan, and Europe. We have about 1,900 responses. We can categorize the invention as having come from R&D or non-R&D, so we're not beginning with the existence of R&D. We can link this to other data sets to measure the knowledge environment and some other characteristics. Here's the model, just because people said we need to have more math in the day. The model is very simple, but the key point is that what we observe here is the ratio of whether, given the invention, it was R&D versus non-R&D. But what we're interested in is, given R&D versus non-R&D activity, what's the ratio of the rates of inventing? And what you see in the sort of bottom here is that the rate of generality will affect the sort of productivity, if you will, of the R&D guys. It will also, the non-R&D guys, and similar for visibility, but we have predictions based on our theories of which of those parameters should be larger, such that if we difference them, the observable, the alpha and beta in these things would either be positive or negative depending on our theory and that's what we'll test, right? So we'll look at the effects of generality on the ratios that we observe. Okay, I won't go into details about how you divide up inventors as having come from R&D or non-R&D. I can explain that. But how common is this? Okay, so I don't want to make huge claims and say the majority of invention happens outside. If we look at what are called important inventions, and I'll give 3 examples, very crudely, about 10% of important inventions come from outside of R&D. What do I mean? In the first one, this is our data, is triadically patented invention. So the firm patented the invention. So at first they patented, and then second, US, Japan, Europe. We get 12% using project level data. NSF, Burtis data, this is firm level data, so it's going to be biased down, and I'll show you why. They got 6% of all patents came from outside of R&D. And then the Aurora et al. Survey, I was also involved in that. New to market product innovations, 11% using project level data. This just shows the share of, among a sort of firms with lots of patents, 15 inventions, at least 15 in our sample. All of these are R&D performing firms. The share of their inventions that were non-R&D inventions, which ranged from 0 to 16%, and the mean was about 9%, which is just to show that there's one, variation, but two, a fair amount of non-R&D innovation, even among R&D performing firms. It also varies by industry. I won't go into how we measure the visibility and generality, but this just compares the invention types. And the first point is non-R&D inventors are on average older at their age of first patent, but often have science and engineering backgrounds. So there was discussion of labor force earlier, and one of the points is STEM education is important for generating scientists and R&D and so on, but STEM education is also important for generating innovative people in the rest of the firm. That's one of the points. Second point here is that there's no difference in terms of product versus non-product inventions in these two samples. And the last point is there's no real difference in how valuable these inventions are. So it's not the case that the R&D are much more valuable than the non-R&D in this sample. Okay, so is it the case that the ratios are as we predict? We predict that general environment should be relatively more R&D, so these are the ratios of R&D against non-R&D, and the generality has more R&D, visibility relatively more non-R&D, and this turns out to be robust to lots of different ways of doing it. Okay, so where are we here? This shows that how modeling the variation in the learning process and incorporating project level data rather than firm level can provide tests of these empirical implications of the various literatures in economics, sociology, and learning theory, and points to some of the limitations of an R&D focused model of innovation, which is, as we said, the canonical one. We also see that, we know that there's a lot of learning by doing and incremental innovation and process innovation in non-R&D, but even triadically patented product innovations, we see the same thing. And basically, the less general the knowledge environment, the more visible the knowledge environment, relatively the more non-R&D innovation you will see. Clearly, there's ways of improving the measures. Some of the managerial and policy implications of this is that this has implications for, if you'd like more innovation, how might you get it? In particularly, how work reorganization, things like lean manufacturing, would affect rates of innovation, because basically it increases visibility. Similarly, choices in technology design can either make the work process more or less visible, which would affect innovation. The cultures of innovation, the degree to which everyone actively participates in producing and also disclosing their innovations. And finally, that if you point out that, for example, manufacturing is an important source of innovations, the outsourcing of your manufacturing function and say, well, I'll just do the knowledge work and we'll make the production work we'll send away, you would be outsourcing at least a share of your inventions and innovations as well. We'll stop there. Thank you.
Let me get out of this there. Now I'm totally blank. Okay. No. Yeah.
Let's see if we can get out of this.
Oh. Thank you. I didn't realize we had another way to control this.
This one?
Yeah.
There you go.
Thank you. Okay, I'm going to talk about something much more theoretical, I guess, about how knowledge travels and ways in which we can tell that a great deal of knowledge is traveling, usually in the form of learning rather than just diffusing. So although we say diffusion models, I mean, that's typical to say diffusion models, it's actually these are more learning models. The difference is the resistance to transmission of information becomes much higher. It takes much more time. It's much more difficult to transmit the information. So I focus on knowledge bridges. What ways are there where we can really convey a lot of knowledge? As a practicing scientist or social scientist, can we really transmit a lot of knowledge? Because typically once you're done with education, people think that's it. They're going to just say, okay, graduate education. But if you're really an active scientist and you're writing a lot and doing a lot of research, you actually keep learning. And I think that's the part of the picture that's really been missing, that the continuing education that occurs just from one's colleagues when you collaborate. So we were focusing today on organizational networks as the bridging part, but also on collaborations between individuals, which are the real heart of it, because information passes from one person to another. So again, we're trying to see how different knowledge pools link up and how that leads to innovation and change. And we look at immediate impacts. This time we're focusing on patenting, which most people have focused on articles. That's where we started out, but we're now focusing on patents as a place for knowledge bridgers because it's actually much harder to tease out the indicators in patents. Also, it's the primary way that firms engage in creating intellectual property. Although now also we see a great increase in firms producing articles as well, especially very small firms. So the impact on overall articles is not huge. But still, as of looking at our whole data base about 10 years ago, I think we came up with about 90% of all patents are held by firms, and it's a little under 70% of all articles are written by scientists and universities. This is just the rough differentiation, but those are the two biggest producers of the two different types. What we focus on is the value of knowledge bridges. Not just the knowledge bridge occurring or trying to predict the knowledge bridge occurring, but rather focus on what kinds of value is really brought about by what's the impact of having the knowledge bridge. So in the piece of research I'm going to discuss just briefly right at the beginning of the talk, we looked at cross-organizational types, so this is the university and firm. We looked at what we're known for as star scientists, the very top scientists that are the top couple of percent at the most of producing scientists. But now we also look a lot at just plain co-authorship along those same boundary lines, realizing but you need to realize in the data that we need to actually trace people that are highly productive. It's not really possible to trace people that produce an article every once in a while and tell even where they are or that it's the same person. So when you're dealing with very large databases, you really need some repeat work product to be able to judge people by, or you have a very difficult time knowing, being able to describe the pattern that we now are saying really is learning and not diffusion. It's not just semantic, because what's underneath that is a very different kind of process. So it occurs more person to person, and that's why we look at the kind of collaborations we do. We look at the inclusion by firms. This is a new measure we're introducing, inclusion by firms of research articles and patents. And the easiest way to see that is to look at the non-patent references section of the patents, which has a great deal of very varied kinds of scientific material typically, including things we're not counting right now, like GenBlast search and GenBank, which is at NIH, which I think GenBank was mentioned this morning in one of the talks. This is the original compilation was done by Los Alamos, and it has all the research articles that report genetic sequences, and now is also basically a protein bank as well. We also looked at I don't really talk about this outcome, but we also looked at the impact on citations to articles and patents, which are the conventional measures for measuring the value of those products. But we focus mainly on the outcomes for small startup firms, both venture capital and going IPO, going public, firms going public. Many of the firms in the database we've constructed are in high technology, because we look at articles and patents, and that tends to be concentrated on the high technology end. So we don't really select out the firms for that, but if we look for observations of articles and patents, this is the data set we end up with. So if we look at the results, the solid lines refer to robust effects that our variables had, and you can see we're looking at government policy, so we're looking at SBIR grants. We're looking at, is a firm using any non-patent references in its patents? The history, we're looking at the history of university scientist co-authors with the firm, and the number of star scientist co-authorships. So this is all scientists from university, all scientists from firms that are working together, not just stars. And the star co-authorship starts with the university, or starts wherever the star is, the university or the firm, and then follows those collaborations. And articles and patents. The citation, you can see the different effects with the solid line being the most robust effect, the little dotted line, possibly, robust effect, and then the very light dot line is just a possible effect. There's one or two significant positive correlations across the different regressions we did, and zero negative coefficients in all of these cases. So we think all of them are possible, and only some are probable or really quite, highly certain. In the regression results I just summarized, you should know we have a lot of other variables as control variables that are not shown in this chart. For example, entry dummies for the year the firm first enters into the data set, establishment age, and year dummies for the end of the regression where not all the patents that have been applied for at the same time are actually granted yet, so we have a truncation of the series. The mechanism we're focusing on, then, the mechanisms are the patent article references. So these are the effects on patent claims. All non-patent references have less impact. Also the learning of tacit knowledge held by others. And this again is the idea that these collaborations, the co-authors or co-invention, increase the rate of patenting and the citation to the patents. So in figure 2, we can see that here patents with any non-patent references and patents with any article non-patent references are both at the top, and at the bottom, with very faint lines that are hard to read in this, unfortunately on this slide, patents with no non-patent references or patents with no article non-patent references are at the bottom of the chart. This means that basically if a patent has any kind of non-patent reference, it gives it a boost in terms of the total number of claims, primary and secondary claims in the patents. And if it has no non-patent references or no article non-patent references, those two lines are very close together. And that means that just having anything in that field gives you a boost by itself, but then there's an additional boost if there's also identified scientific articles in it. The rest of my presentation is really going to be more or less graphical, but in terms of not going back to a lot of words, I hope. There's a few put in every once in a while just to give some clarification, but in the next charts we see that the firm scientists with co-authoring or co-inventing ties to universities are much more likely to patent than firm scientists without those links. So if you can compare firm scientists with prior patents and university ties at the top, firm scientists with primary patents but no prior university ties, and so on. So the magnitudes of difference are pretty large, and we found it quite significant in the work we've done so far. And next one shows you university scientists, and again, there's even more effect, if anything, because university scientists have seldom had any exposure to patenting before. And during this time period, that's when it becomes, that's when universities begin to patent their own patents. And so you can see that there's a learning effect in terms of transfer of knowledge to university scientists who are learning to patent. Oops. So what about the scientific collaborations in patent inventing? I think the easiest way to show this is through maps. So I'm going to go ahead and start this. So it's, when you get onto the map, you'll notice that the firms that patents are squares, but this goes pretty fast. It's actually a moving image. Firms that patents are squares. Universities that patent are circles. And unfortunately, because universities patent so much less than firms, there's a bit of a scaling problem in the maps. And they look more similar the whole time, but they're actually showing the same progression, type of change, magnitude of change as the firms. And then the total number of co-published articles are the triangle. And it's kind of fun to watch the map take off. So you can see the triangles grow. Notice the great growth in the number of triangles. Right there, it tells you a lot right there. That is, you don't make that kind of investment. It's very difficult to make that kind of investment, to be a co-author of an article, unless there's a real payoff to what you're doing. These articles also tend to be really highly cited. And especially, I know this for sure, and with very careful research that we did in the biotechnology field, that these articles often outpace the other articles at either, in any kind of setting, including the university. They were among the most highly cited university articles. This will just keep playing on infinite. I'm going through its little sequence until I get out of it. Oops. Go. Oh, it's not going to the next slide. This one? Okay. So we're combining ideas on intellectual property. And I'm just going to skip to the next slide, which is the figure. So if you look at the top, these are the things you're used to talking about, and I've been talking about them now, the patents, the articles, that are in scientific literature. So normally we focus on what's already codified, what's already accepted as an indicator of intellectual property. The articles are more informal in the way they're enforced than patents, as we know, because the scientific literature largely rests on priority claims, whereas patents, the scientific literature feeds into non-patent references. But, and that way it has an effect on the actual property rights of the patent that was shown by claims, because claims are the key list of the property rights that are legally binding for the firm. So of course they want as many claims as they can get. So if working with the university scientists will produce this, guess what they get? A lot more publications, and mainly with university scientists. Though you also see plenty of articles that are also by firms themselves, but they tend to be a bit more applied. I'm going to focus just for a moment, though, on the de facto IPRs. Yeah, and just to say one word about the very bottom of the whole chart. These are latent, and copyrights and trademarks. I'm sorry, that there's breakthrough tacit knowledge, so the second one in the chart. Breakthrough tacit knowledge involves natural excludability, and that's what we're really looking at for the most part. This really early period of knowledge where there's a great deal of protection just by others not having access to the information yet. Very little has been published. Think about the beginning of biotech, think about the beginning of nanotech. Early on, very few people could enter. And I'll stop here without my conclusion slide because we're trying to keep it. Oh, should I do that? Okay. Okay, conclusions. Patents greatly benefit from science input. So we see that it increases the importance of more tacit forms of IP because articles then become much more important in getting property rights for patents. And natural excludability yields more claims on average. The idea that some of these scientific ideas can't just easily be picked up from what you see on the screen, but actually, or in an article. And then what you really need to understand the underlying mechanism the person is thinking about and get deep into that part of the science before you can do it. It's also an incentive to firms to work with scientists and in fact to actually engage in their own scientific advances. So we see more publishing by firms, much more publishing by firms, or publishing by many more firms is really the way to say it, maybe. Because, again, many are very small, so the publishing may not be big compared to a university, but the relative rate of change is very high. Next to open science, the best thing is disclosed science. So sometimes, well, sociologists especially, and that's my first discipline, with economics being kind of my second discipline, that we know that often academics look askance at the idea of patents, and in the social science that's especially true. But here we see that it's another form of open science, and actually the two benefit from working together so that articles are more highly cited when they're written with firms, typically. And so we think of property rights here as just creating more new science. So therefore, if the new science is still open, we're actually adding to the what's open and available to everybody. And firms are now producing more of that kind of knowledge. So I end on that note with the hope that this really means that there's real improvement. Okay?
Okay, let me begin by sharing a bias. Invention is the creation of a new process or device. Innovation is creation of change in the marketplace. The vast majority of inventions never contribute to innovation. So I'm talking about change in the marketplace. I'm going to talk about human-centered design. When I define it in a minute, you'll see why that's important, how it compares to other approaches. We're going to talk about a particular visualization as an example, and we're going to talk about a whole bunch of case studies. In fact, the human-centered design methodology I'm going to talk about here, we've used several hundred times with firms throughout the world, most of whom you would recognize. And then come back with what did we learn? What did we learn about innovation from those experiences? So, in the late 80s, we were working on inventing new software technologies for commercial aircraft cockpits. And we worked very carefully with commercial pilots, and they were very happy with what we were doing. It was considered very human-centered. But we made a discovery that just because the pilots liked it didn't mean it would make it onto an airplane. Because the pilots don't design the airplanes, they don't manufacture the airplanes, they don't buy the airplanes, they don't regulate the airplanes. So it struck us, there were other humans in this process we had to be concerned about, not just the user. And that's where this notion of focusing on all the stakeholders in the design process became important. There were three clusters of issues we identified with the stakeholders. One was related to validity Do they perceive your solution as actually solving the problem? Another is acceptability. Do they perceive your solution as fitting in? Is it a way they'd like to do things? It could quite possibly be valid, but they just don't want to do it that way. And finally, is it worth it? Do the methods and tools provide the benefits that are worth the cost of use? And costs here include not just the purchase price, because only one stakeholder writes a check. It's also the cost and the effort needed to learn and use the solution. Now, what's the limit of existing approaches? And here we're using models, simulations, visualizations to help companies make major strategic decisions to put new products in the marketplace, to help universities make decisions to change their strategy, to help government agencies make decisions to allocate their research portfolio, for example. In general, they're concerned that the sponsors of modeling efforts complain they take too long and are too expensive. I was giving a short course in South Africa quite a few years ago, and one of the people in the audience from a government agency was very excited about what I was presenting. And he came up to me and he said, could we use your approach to solve his problem, which was related to the chemical industry? And I said, yeah, it would work. He said, I said, when do you need it? He said, tomorrow. Okay, the whole prep work of developing a model and simulation is usually a lot longer than 24 hours. Acceptability. Many key stakeholders and the types of problems they're interested are not educated in modeling and simulation. So they don't, it's all just a magic box as far as they're concerned. So we had to focus on visualizations to help them understand what was going on. And validity, it's very easy for assumptions to be inconsistent across component models. Coupled states across component models can lead to incomputable or unstable computations. The worst case is you get an answer and it's dead wrong. So how do we overcome these limitations? Again, we're using models and simulation to help companies and agencies make major strategic choices. First of all, in the red is what matters. You need to avoid over-modeling. There is a tendency in engineering to include every possible detail you could. And what happens is not only your customer loses track of what's going on, so do you. So we start usually with very simple models. We want to immerse key stakeholders in interactive visualizations of the phenomena. We can't immerse them in the equations. We can't immerse them in the software code, but we can immerse them in their world and let them explore, as you'll see in just a second. And finally, explicitly address the model composition issues, the kind of problems that can go wrong. So here's the immersion lab at Stevens. This group of healthcare consultants is working in this room, and this is a simulation of the New York healthcare ecosystem. 66 hospital corporations. Each of the agents, the hospital corporations, has balance sheet, income statements, quality metrics, operational performance, et cetera. And we're looking at the evolution of the New York ecosystem. Because of the Affordable Care Act, we're going to go from 66 hospitals down to about 20 in 10 years. And the question is, who is going to end in the 20, and it depends a lot on what each of them does, and this group is just experimenting, exploring. We're not predicting that any particular hospital will be in the 20, although we're pretty comfortable with the prediction that it'll be only 20. So let's talk about the hundreds of experiences we've had in this kind of environment and similar environments. The visualizations were the key. The people in the room who are unfamiliar with modeling and simulation, but can get up and take the controls, and we like to say they can fly the future before they write the check. They fly the future that causes them to buy into different scenarios and feel ownership in the solution. So let me give the highlights of some case studies, and I mainly want to focus on the lessons learned. So we've done these studies over the last many years in these 4 broad areas. Some examples in business planning, products versus services, defense companies converting to other marketplaces, R&D as a service, academic strategies, new product planning, automobile engines, microprocessors, digital signal processes, medical imaging systems, technology investments, random access memory, optical computing, unmanned air vehicles, licensing technology. Sometimes people have developed technology, or inventions, if you will, that they don't need. So how do you look at selling that to other companies? enterprise transformation, how do you understand opportunities, understand deficiencies, how do you deal more recently with population health initiatives and the Affordable Care Act. So these 16 are examples of activities we've taken about. I feel a little bit less like Isaac Newton with some of the things we've heard here, and more like Charles Darwin and just sailing the enterprise seas and helping people to deal with their problems. And here's what we've learned in 3 areas. And then I should mention, most of these things are documented. These experiences led to these companies investing many billions of dollars, and in some cases creating multi-billion-dollar companies that they sold. Okay, starting assumptions. When you go into an effort of trying to help a company to innovate, usually with technology, but not always. First question is, who are the stakeholders in the problem of interest and its solution? And it's not just the consumer. There's a lot of other people that have to be aligned to make innovation happen. Second, you need to look at the problem and solution from the perspectives of the stakeholders. And the best way to do that is to interact with them and understand what they feel is important. Let them react to prototypes, tell you why it's wrong, tell you why what they thought they needed that they told you isn't what they need now that they've seen it. Articulate and validate assumptions. Basically put down explicitly what are you assuming about the stakeholders, about the economy, about the technology, et cetera, and try to validate those. And then understand how other stakeholders may act. In fact, one of the things we did most often was once we have a plan for your new semiconductor or your new aircraft engine, et cetera, that you're going to put in the market, we would change hats and say, okay, for the rest of the day, let's just be your competitor. And you put that out in the marketplace. What are you going to do? And so we would role play the competitor, and basically often it was very interesting that the competitor would not comply with your strategy. So I remember in one case, I asked the senior people involved, what do you think the competitor is going to do when they see your new 3D imaging system? And they said, well, they're going to have to embark on 2 years of R&D to catch up with us. I said, okay, let's use our tools and see what we would do if we were them. And they basically concluded they would cut their prices by 15%. And the people in the room actually said, that's not fair. Okay. Framing the problems. Define value very carefully. One of the problems I found in the 2 software firms that I ran is people would define value. The engineers, the software engineers, not the marketing people, but the software engineers would define value in the sense that the people got our software. They bought our software. Well, that was value for us, that they wrote us a check for the software. But the real question is, what's the benefit of having that software and really understanding that in depth? Think in terms of both current businesses and possible future businesses. We've done a work with many companies on trying to understand what your current success puts you in position to do in the future. What kind of technology options are you creating for your future where you can go into other markets and provide other solutions? Consider the possibilities of customizing solutions for different customers and constituencies. And maybe your underlying platform is the same for everybody, but for each customer base, each corporation, it appears totally tailored to them. And it certainly is in look and feel. Access and integrate available data sets. And this is becoming more and more popular now. You have a variety of data sets you can put into these tools and these models where people can access. And this is very important sometimes when they question the outputs of the models, that you can actually peel back the onion and see what's the underlying data that's causing that result. And this usually gives them much more confidence. Your plans need to also include strategies for dealing with legacies. Legacy organizations, legacy systems, legacy solutions. Because often your new thrust has to live in that organization. And so we've had many cases where the new technology was basically launched in a garage down the street with this unusual label on it. No one had the slightest idea what it meant, but they didn't want to impose the whole corporation on the new venture. And that seemed to make a big difference. Implementing solutions. One thing we found working with companies, it can be great fun to pursue market and or technology opportunities, where you can think of whole new products and services and solutions and draw upon data, models, and other techniques. In stark comparison, crises are not all that much fun. Basically, where the company has waited too long, they have some innovative or inventive ideas, they no longer have the resources or the energy to really make it happen. Plus, they're using all the resources to keep the existing organization running. I've asked many senior executives, what's the problem that keeps you awake at night? And most common answer by far is, my biggest problem is running the company I have while I try to create the company I want. Because the company I have is consuming all my resources. The existing enterprise can hold change back. You could be fighting an immune system that doesn't want to change. And so what that requires, we found, is really good storytelling about why are we going through this change, where are we going, what's it going to look like from the train while we're going there, in order to get everybody to commit to substantial change. Now, the last lesson here, I've often worked with companies where they say, we've gone through enterprise transformation, we've changed everything, we're all set to go to success. And I say, well, my first question then is, if you've gone through a transformation, what did you stop? Because if you haven't stopped anything, you didn't change. And that usually takes people back, because it's actually so easy to start new things. It's actually so easy to start them under-resourced, where they're going to have a very hard time succeeding. But making the tough decisions to decide we're not in the buggy whip business anymore is much harder to do. So in summary here, my data is just a few hundred experiences. I don't have any. I do have published a few papers with data from these working groups, what they value in terms of support, what they seem to need to increase their confidence and their productivity. But nevertheless, this is really observations on just working with these executive teams and senior managers over the years and helping them to try to turn their inventions into innovations. Thank you.
Having run a relationship here, we have time for questions, comments about any of the ways we're turning ideas into actual products and processes, which is what this was all about. Yes.
So this is a question to the first speaker. You had a slide that showed that the non-R&D and the R&D by firm. I looked at that real quick, and it looked bimodal. You either had less than 5% or more than 10 or 11. Have you looked into that possibility that firms really are more bimodal in terms of whether or not they even consider the non-R&D as an element? I mean, I just noticed it on your data. I was curious.
Yes, that's actually a nice observation. But anyway, we didn't specifically look at that point. The part of what you're seeing there is probably there's a big industry effect. I mean, that's sort of our main point, is that the main effect is because of what business you're in. But we also suspect, and in one of the models, we actually put in firm dummy variables to control for these kinds of things. But what you're alluding to is that we suspect, and this will be sort of follow-on work, that there are firms that are sort of strongly encouraging the development of innovations coming out of the non-R&D parts of the firm, and other firms are either not encouraging it or, like one of the examples, actively discouraging it. And we would, think that you're right, that that's a space for, either managerial or policy intervention. Yes.
All the user-based innovation that Von Giffen did and the rest of that.
Right. I should just clarify. This is not user-based innovation, because these are all innovations generated by the firm that produces the innovation.
From
Right, but that's different from just to be clear. Yes, but again, there's an important difference there, but it's an interesting point. Yes, yes.
Ben Schneiderman, University of Maryland. Thanks to all for interesting presentations. My focus is on Lynne Zucker's work. I was particularly pleased to see you're reporting that papers which were published jointly of firms, you called them, and university people got apparently higher citation rates than others. And could you tell us why you think that happens? It's sort of the interesting point, and you know, it's the point I'm trying to make, but trying to shift the culture is important, and so I want to understand why you believe that is out.
And I haven't really tested all the reasons fully, mechanisms that could lead to it. But I would guess that one of the main ones is that they're interested in the movement of science forward, and they therefore are really trying to push the envelope even more. You know, there's some scientists at the university that are also pushing the envelope, but the union of the two means that that area gets pushed even more. The other thing that might be happening is because there's a lot of new startups, a lot of commercialization taking place, those articles get a lot of attention because everybody's looking for clues about how you get into this whole system, the scientists that aren't yet in it. So there may be some gaming of the system to try to make your paper look like it's very relevant to companies, even if it isn't, by citing ones by this by firms. But the majority of the ones that are really at the leading edge are going to end up being joint between university and firms. So it could be an underlying game of some type.
Well, I think you're getting to the rather radical idea, which I support, which is that working on real problems makes academics better theoreticians. Yeah. That actually you get deeper solutions, that more publishing happens, but I mean, the data don't really tell you whether solutions propagate, but they tell you that the ideas propagate. And so I'm sort of supporting your notion, the radical notion, that working on real problems gets you better theory and better papers.
I think also you end up with more money more easily, because I know one of the people, we did a tremendous amount of interviewing, and one of the people was especially emphatic that he was at the vice president's level of one of our of a major biotech. He was especially emphatic about the idea that he spent a third of his working life as a professor writing proposals. But then he went to the firm and he writes a 2-page proposal, a 3-page proposal, that's all. I mean, it doesn't really take up any significant amount of his time, and yet he gets even more money.
Well, that's valuable, but money doesn't buy you citations.
No, but
it shows that
your target more quickly, and when an area is the forefront's moving very fast, you want to move very fast.
So, my conjecture is that academics are smart people. They just don't know how to choose good problems. But if they work with people who have real problems, they do a lot better.
Yeah, or you get people that actually both know how to work on good problems, but the intersection winnows out some that aren't winners from one perspective or the other, so you end up with a better set.
Great.
I think both come together.
I think it's great. Just watch out, because what you're saying is radical.
Oh, well, I've known that the whole time. I know I'm always in danger, especially from the social scientists kicking me out as a member.
Hi, Michael Darby. I'm not going to ask my co-author a softball question. It said again for the first author. Your examples were sort of lower level employees outside of the R&D. But a lot of the firms we've studied in terms of the entrepreneurial firms, there's a creative genius who really is what makes the firm, be it Steve Jobs or in other creative areas, René Lalique. And they're usually not in the R&D department, even though they may be on, like Jobs, 159 patents. They're usually in the G&A. And so it may be in part that your non-R&D are in fact really kind of the head of the R&D at the CEO or chairman level. So I just wonder if you've looked into that.
Yeah, that's a good point. Since we were very tight on time, I didn't go into a lot of detail on how we categorize these. But very roughly, the way these are categorized is that we have two questions. The first question is, where are you working, which is what you're sort of pointing to. Or am I in general administration, or am I in R&D, or am I in manufacturing or sales or something like that? But we cross that with, what was the process by which this invention was created? And this includes, it was part of an R&D project, it was the goal of an R&D project, it was an expected outcome of an R&D project, it was an unexpected outcome of an R&D project, or it was my normal job, which is not inventing, or sort of pure inspiration. And the key point there is, even if you're not in R&D, but you said that this was related to R&D, you know, an R&D project, we define that as R&D. So it's the people who aren't in R&D and the project that generated this was not an R&D project. Those are the people we're calling non-R&D. And then it turns out, if we divide it in other ways, it's actually fairly robust. But yes, you're right. There's a lot of people who are not. So for example, it's very common to have a kind of team that consists of some people in R&D and some people outside R&D, for example, in the sales division, that are, you know, incorporating advice they got from users and so on. That would be called an R&D project in our data. It's the non-R&D guys are the guys who are themselves not doing an R&D project and are outside of R&D, but are making invention. So yeah, but that's a good point. Thank you.
We will win the prize for ending slightly earlier than anticipated, and I think that gives a good break for the next period.
Yeah, the reward is everyone gets coffee and a brief break.
I was going to demand more for our.
Okay, I will ask my question later on. But before you get coffee, we have our group photo. So you're not done yet. So let's use that. But first of all, let's thank the panel